Thank you very much. I'm very glad to have a chance to talk here. And just 3 minutes ago, I was really nervous because I was failed to move my slide from my computer to here. So I succeeded just 1 minute ago. Okay, so I'm going to talk about some wedge operation on toric orbifold. Already Hanchal talked about very nice overview about wedge operation, so probably many of you are familiar with wedge operation. Okay, so this is the joint work with Tony Barry and Somen Saka. This is my setting. So T is the k-dimensional real torus, and X is a topological space with torus section. And so probably we want to calculate some. Yes. I'm sorry if you don't want to compute this, but anyway, we want to compute this kind of topological invariance. So as far as I know, there are several tools to compute this cohomology, generalized cohomology theories, like this sequence and spectral sequence. But behind the actual computation of this cohomology theory, if you can assume that R degree cohomology vanishes, then something becomes very easier than before. Easier than the case without this assumption. Okay? For example,
색깔이 자꾸 깜빡거려가지고.
Okay, so for example, Chang-Shelby sequence is going to be exact if we can assume this. So which gives you some GKM theory, something like this. And then this, for example, this Atiyah-Hirzebruch spectral sequence connects this generalized cohomology theory and singular cohomology in each E2 page. So if we can assume this, then they collapse in E2 page so that every computation becomes very easier. So and also there are many nice families having this kind of property in many areas, like some symplectic category. If the manifold is Hamiltonian, if the manifold has a Hamiltonian Lie group action with isolated fixed point, then our degree cohomology vanishes. And some homogeneous space, some semi-simple Lie group quotient by some subgroup contains maximal torus, which gives you the Schubert cells, which consist of even dimensional, which gives you the R degree cohomology vanishes. And also, this is inspired by from Zhang's talk, some toric origami with a cyclic origami template and co-orientable yes, co-orientable folding hypersurfaces. They have vanishing O degree cohomologies, and then probably this category has much wider class introduced by Professor Masuda and Panov, some torus manifold having face a cyclic orbit space. And also quasi-toric manifold or smooth toric varieties, their cohomology vanishes in even in R degree, right? But if we slightly generalize this category to orbifold, then O degree cohomology may not vanish. For example, this is just simple 4-dimensional toric variety. So this is a 2-dimensional fan, and I'm just put primitive 1-dimensional arrays like A1, B1, A2, B2, A, and Bm. And then if I compute cohomology, then, I'm sorry, this is 1 maybe, I'm sorry. So this is 1. So Z0 and some free part, and they have torsion in degree 3 cohomology. So this P is detected by this one-dimensional arrays and then just compute determinant of this each 2x2 square matrix and then compute some GCD of this, then this integer is going to be this P. So, and also, if you ask me how to compute this cohomology group, then long time ago, Jordan and Fishley, they construct some spectral sequence which just come from fan data. And you can compute E1 page and then differential gives you, in some nice case, they collapse, and then if you compute a little more, then you can compute these cohomology groups. So, in this business, it's very natural to ask whether a toric orbifold or singular toric varieties, whether they are, is there any necessary or sufficient condition for O-degree cohomology balances? Right? Because we have example which has vanishing O-degree cohomology and which does not vanishing O-degree cohomology. For example, if you just look at the weighted projective space, they have vanishing O-degree cohomologies, and then they have same cohomology groups with just usual projective space, but ring structure is totally different. And also this kind of very simple example which does not vanish on O-degree cohomology. So there are several papers corresponding to this problem, but as far as I know, this the Kwata, Matsuda, Cheng, this paper is most generalized version on this business. They gave the complete answer for four-dimensional torus orbifold, which torus orbifold is much wider class than toric singular toric variety, which has orbifold singularities. And they gave some necessary condition for arbitrary dimensional torus orbifold. But as far as I know, there is no sufficient condition for checking whether this cohomology vanishes in our degree or not. So today, I'm going to talk about how we attack this problem, I and my collaborators. Let me just tell you some setting. This is our ingredient to construct toric orbifold, and probably Sunjung in yesterday's talk, she gave exactly same ingredient to produce quasi-toric manifold. But the only difference is this one, determinant of at each vertex. We can collect n. Because this polytope is simple, so we collect n different primitive vectors, and if we form a square matrix around the vertex, then we can compute the determinant. If this determinant is 1 or -1, then it produces a smooth space. But if you allow not just non-zero, then it gives you some singular point, which gives you toric orbifold. And okay, so this is just for technical reason. And this condition is for at least we pass this necessary condition. Okay, so so their necessary condition corresponds to whether this image of lambda spans the whole lattice or not. So people usually describe this characteristic pair. We call this characteristic pair polytope and characteristic function. Anyway, people usually describe this characteristic function by this simple shape, and then some algebraic geometer enjoys this fan description. They are in a sense they have same information. So definition of quasi-toric orbifold is first you take a product of torus and polytope, and then take a quotient by some equivalent relation given by this characteristic function. But there is another construction for toric orbifold, like probably Sunjung explained about the quotient of moment angle manifold by certain torus section. But But as far as I understand, this quotient construction is more comparable with other areas like algebraic geometry or symplectic geometry, because these are some topological model for symplectic reduction or GIT quotient in algebraic geometry. But this construction has some benefit to see what is the inverse image of the OB space. So little easier to compute, because this Tn acts on this toric orbifold by the product multiplication on the first vector, and then the orbit map of this action is just second projection. So somehow it is easy to little easier than the moment angle complex quotient construction to see what is the pre-image of this OB space. And also, if you take a face of P, its inverse image is another toric, quasi-toric orbifold. This is very key fact in my talk. Okay, so this is my setting, and then let me tell you how we attack this problem. We first consider certain sequence from the original polytope. Instead of giving the precise definition, I'm just give you the example. Okay, so first, this is my original polytope. Okay, and then I take a vertex here, and then delete all the face contain this vertex. So I just consider this polytope as a polytopal complex. That means as I said, I collect all the faces, vertex, edges, and two-dimensional face and three-dimensional face. And then deleting faces means if I take this vertex and then delete this vertex and these three edges and then these three faces, and then the remaining things is going to be this shape. Okay? And then I'm going to do the same operation on each polytopal complex. Also, one key limit is there are several vertices like this, but I'm going to choose one of these three, because the specialty for these three vertices is nothing but they have local neighborhood diffeomorphic to Rn positive. But in these three guys doesn't have, they are locally not look like some Rn positive. Okay, so I'm going to do this. For example, if you come here, then what you have is 1, 2, 3, and 4 candidates to go through. Okay. Sorry. Okay, so this if you dualize in a simplicial complex, then this operation is some sort of shelling in a simplicial complex. So probably this operation, we developed this operation, but probably this has very strong connection with shellability in simplicial complex. So the geometry interpretation of this retraction sequence is taking this kind of vertex is nothing but if you cut this vertex, then you get some simplex. Okay, so a simplex, and then you have a natural projection from this simplex to the remaining next term. The just straight line map, right? So from here, if you just connect this V, if you take a point here, then take a straight line, then it reaches one point in the remaining part, and then this gives you some map from this simplex to this one. And then you do the same operation in the next step. For example, if you cut this vertex, then this gives you one-dimensional less simplex, and then take the straight line map, and then this shape gives you this yellow part, and then to the next term in the retraction sequence. Okay.
So in the retraction sequence, you don't care the dimension where this one is R plus to the some power.
Yes.
But sometimes you have some choices which has, let's say, higher dimensional pieces but lower dimensional.
We don't care. We don't care. We don't care. We don't care. Yes. Just anything. Some are N positives.
So anyway, try to retract.
Yes, retract continuously. Okay. So, okay, so this, if you regard these guys as an orbispace of a given toric orbifold, then inverse image of the original polytope is going to be the original toric orbifold. And then the remaining face, if you take the inverse image, then this is nothing but the lower dimensional toric orbifold and then their unions, right? Just a face of unions. Okay? And also, the pre-image of the simplex obtained by cutting a vertex, then this is this orbispace. This orbispace, then they take an inverse image, then this one gives you this kind of space according to my definition of a toric orbifold. And then this is known to be some r-dimensional sphere quotient by some finite group. So this kind of theory is developed by Professor Seo and Sakar. But our definition is slightly more generalized than theirs, but essentially they are same. So this space corresponding to this quotient of all-dimensional sphere quotient by the finite group, and then we call this orbifold Lens space because usual Lens space can be obtained by this kind of idea. Okay, so probably some people can guess that you can compute this. Since this is finite group, so we can compute this homology by transfer homomorphism. Okay? So not exactly, but we can guess what kind of torsion can exist. Okay? All right, so these three spaces are connected by some, in a nice way, in a core fiber sequence, like this space, and then this space, and this space, they form a core fiber sequence, and then this says that this original toric orbifold is a mapping cone of this map. This F is induced by the map which I described before, the straight line map. Okay? So, all right, so let me be more precise. This space is this yellow part times torus some quotient relation. And then this is simplex times torus quotient by relation. Right? So this straight line map gives you the map from simplex to this yellow part, and then take a product and quotient of the Davis and Januszkiewicz relation, then that gives you the map from here to here. And then finally, this xp lambda is mapping cone of this map. So if you do real excision, some basic algebraic topology technique, then this relative homology group can be identified to this orbifold, homology of orbifold Lens space. Okay, so okay, so if you look at this is another toric orbifold. So you can do the same computation, same core fiber sequence continuously, right? So this one, and then these two slides look same but a little bit different, right? So P and lambda, and so another core fiber sequence obtained from in the middle term of retraction sequence. Okay? So you can do the same computation. So, and finally, you can compute, in order to compute the homology of this original toric orbifold, you just consider the long exact sequence of this pair, at each step, and then if you, long exact sequence gives you these two parts, and then these are isomorphic to this the reduced homology of orbifold Lens space, and then by transfer homomorphism, if they have some torsion, then it has to be this amount. Okay, and then in the middle you have these two guys, and this is our goal. And then you have to know what it is, but this can be analyzed by doing the same core fiber sequence continuously. Okay. So this is our main theorem. Well, this is the sufficient condition for checking whether its cohomology concentrated in even degree and torsion freeness. So this is purely combinatorial. You just analyze the retraction sequence and then collect all the possible shape, and then if you can assume that these singularities are their GCD is equal to 1, then whatever you take this type of long exact sequence in the middle, it has to be torsion-free, something GCD argument. Okay. Right. So, for example, so this is weighted projective space case. If you start from a simplex, then the simplex, so just forget this. If you choose one vertex here, then the remaining thing is another simple lower dimensional simplex, right? So, for example, if you just start with very complicated polytope, then retraction sequence might be very complicated. It is very difficult to analyze. But if you just a simple polytope, like simple polytope, like simple polytope, like this way, so that that means it has many symmetries, so that whatever you cut, you probably if you can get some similar shape of polytopal complex, then it is possible to analyze all the possible retraction sequence, right? So, for example, the most simple polytope is the simplex. I'm sorry, very so many simplex. Okay. But anyway, whatever you take a vertex, anyway, it's going to be another simplex. And then, if you remember how to get the reduced characteristic function from the original one, then you take a quotient and then take a primitive one, which gives you all the GCD of these lower vertices. They are 1. Okay. For example, the basic idea is in particular this weighted projective space case. If you have a weighted projective space with weight 1, 2, 4, 6, something like this, then you can mod out by 1, 2, 3. Right? So if they have common GCD, then they are homeomorphic weight in weighted projective space. That means, for example, 1, 2, 4, 6. If you cut this one, then 2, 4, 6, they looks like GCD is not 1. They have GCD 2. But finally, this weighted projective space with weight 2, 4, 6 is homeomorphic to weighted projective space with weight 1, 2, 3, so that you can make GCD is equal to 1 always. Okay, so well, in this case, but this is another example which is non-trivial. For example, if you take a prism and then I'm just give the characteristic function like this way. And the P1, P2, P3, and Q1, Q2, Q3 are all different prime numbers. Then, the reason why I take this one is, at each point, the singularity is P1, P2, P3, and Q1, Q2, Q3 if you compute the determinant. Okay? And then analyzing the retraction sequence. This is one example, but since this simple polytope is quite simple to analyze retraction sequence, and then all the possible shape are something like this. And then whatever you take, you have more than 2 this kind of vertices. So if you expand a long exact sequence like before, then for example, this vertex and this vertex, 2 different co-fiber sequence, and then if they have torsion in the middle, then they have to be GCD of these 2 guys, so that you can conclude GCD torsion. It has to be torsion free, and also you can compute R degree cohomology. Okay. I think many of you, your face is on present, but I'm sorry. Okay, so, but anyway, okay, let me continue. Any questions? Probably many, but later, I'm sorry. Okay, so, but anyway, we can give some sufficient condition for vanishing O degree cohomology and torsion free purely combinatorial way, even if it looks a little difficult, but anyway, we can check by hand or computer. Okay. So I'm going to apply this theorem to wedge operation. Okay. So wedge is a way to produce new characteristic pair from the original one. And then so Hanchal already gave very nice overview, but in a polytope, if you just focus on the polytope, then the original polytope and then take a product with half ray and then just cut by hyperplane like this. Then this hyperplane is chosen by, if you take a facet here, then hyperplane is the hyperplane containing this face, this facet. Right? For example, I take this facet here and then take a hyperplane containing this face and then cut, then this gives you this kind of wedge or polytope. And then it is, so if you look at this wedge, then you have two copy of original polytope in this shape. So it is natural to give the index of the facet like this. If this is Fi, then two copy of the original polytope is P plus and P minus. Okay, this is just my choice. And then F1 prime, Fi minus 1 prime are facets given by the original facet. This triangle, and here is rectangle, and then triangle. Okay. And also, Hanchal didn't specify how to put the characteristic function, but the original, I don't know what is the original, but Bari and Vendersky, Gittler, yes, BBCG, they specify some how to give the characteristic function on this wedge of polytope like this. I'm going to explain what is the specialty for this special way to give the characteristic function. But all right, so this is an example. If you start from a one simplex and characteristic function 1 and minus 1, which gives you the usual projective space, two-dimensional projective space, and then take a wedge, then it gives you the two-dimensional simplex, like take a one simplex and then product with half ray and then cut, this gives you a triangle. And then the characteristic function is given by this way. So if you look at this, 1 and minus 1 exist here. And then one more wedge, this exactly same characteristic function exists in this part, right? So this means projective space gives you, if you take a wedge, then higher one-dimensional higher projective space appears. Okay. And if you take a wedge of Bott manifold, then it gives you generalized Bott manifold, and then you can produce many new other Toric manifold from the original one. And why people consider wedge, then some people use this wedge to classify some topological space, but this wedge is another way to produce a new Toric manifold or orbifold with similar property. This similar has many meaning, but somehow some cohomology ring can be easily read off from the original one, something like this property. And then together with some theory of polyhedral product, then they claim that a toric space with less combinatorics in a sense, because higher dimensional projective space come from this one simplex and 1 and minus 1, so something like this. So in order to, in some nice class, in order to analyze the Toric manifold, we have to analyze the characteristic pair whose polytope is half dimensional, but sometimes lower dimensional polytope gives you all the data, right? Right. So if you apply this wedge operation to orbifold, then this is one canonical example. If I take a P as a simplex and characteristic function is given by this property, then it gives you some weighted projective space with this weight. So this equation gives you chi I here, and then if you take a kernel of this characteristic matrix, then this chi 1 through chi n gives you exactly the weighted circle action on Tn plus 1, so that this is nothing but the sphere quotient by weighted circle action, which gives you weighted projective space. Anyway, if you take the wedge of this characteristic pair, then the polytope is one-dimensional higher simplex, and then characteristic function satisfy this long equation, but they are all same, but one copy of chi I here. Okay? So one-dimensional higher weighted projective space, but one double weight here. Okay? So in a sense, like I said before, this weighted projective space and this weighted projective space, in a sense, they are similar. Okay? So one proposition is this, in the sense of orbifold, this special wedge operation doesn't produce any new singularities. If you collect all the singularity and then take a wedge, and then they have exactly same singularity, exactly same different kinds of singularities. For example,
Same dimension or singularity?
My singularity is the index of a local group.
So it's all okay.
So, for example, okay, so this is canonical example. So all the possible singularities are chi 1 through chi n plus 1. But here, even if we have one more singularities, but they are chi 1 through chi n plus 1, there's same kinds of singularities. Right? So if you take a simplex and then take a wedge, then exactly these two vertex have the same singularity. Because this happens because of our special choice of characteristic function. Okay? So that my similar means somehow we can guess, we can expect that whether the original polytope has satisfied our GCD condition, then the GCD totally depends on this kind of local computation of local group index, and it doesn't produce any new singularities. So it is very natural to guess or expect that the original polytope, if the original polytope satisfies the GCD condition, then the new characteristic pair satisfies this GCD condition or not. Okay. So
originally all the singularities are isolated, right?
Yes.
So the wedge product does not increase the singularity dimension, just they still give you isolated singularity.
So my singularity is singularity at each fixed point. So in order to expand the long exact sequence which I showed you before, you just choose the vertex on a polytope, right? So if the singularity exists in the co-dimension two polytopes, but if you just say singularity, then it could be connected by the co-dimension two faces of the polytopes, but the singular locus maybe. But I'm just focused on the singularity of singular point of the vertex, the point corresponding to vertex of the orbit space.
So did you make the singularity the higher dimension, they have connected? They can be connected possibly? But after wedge product. After wedge production.
Yes.
So here V3 becomes V3 minus to V3 plus, right?
Yes.
And then what about this edge from V3 minus to?
They don't have singularity on this whole space. The singularity exists in co-dimensional two phase. So in this particular case, they are all isolated singular point probably. But if you go to higher dimensional, then if you collect all the point which has singularity, then they are connected. Yes. But I'm just looking at the point, the vertex, to expand the long exact sequence which I showed you before. All right, so this is my question, and then this is an example of wedge operation of 5-gon. And then the way how we analyze this space is just a cut of a vertex or cut of a vertex of the original polytope, and then finally it becomes this kind of simplex times the I because of a wedge, because the wedge operation, you take a product with the half ray and then take a cut by hyperplane. So sometimes this kind of simplex, if this vertex contains in the original facet which I chose in the original polytope, or it becomes some simplex times I if this original polytope is original vertex is not does not contain in the facet which I chose to take a wedge. Okay. So cut this several spaces like this, and then probably you guess that the preimage of this simplex is another orbifold length space, and then this space, the inverse image of this space is nothing but the orbifold length space bundle over the CP1. Okay, so this is the lemma which we could show. Some space is orbifold length space, and then some space is orbifold length space vibration over S2. But anyway, this space, we can compute the cohomology from the transfer homomorphism, and so that we can guess what kind of torsion exists. And then we can use the spectral sequence because they have vibration structure. So you can use the spectral sequence to compute the cohomology groups. But anyway, the main idea is they don't produce any new different kinds of local group index. So in this example, we can, this simplex gives you some higher dimensional orbifold length space, which have the same, the finite group, this finite group has the same index with the original one. And then this is the orbifold length space vibration over CP1. We can compute the cohomology or homology by the spectral sequence. Okay. So, yes, and then we decompose this orbit space by the several way and then compute the Mayer-Vittori sequence or something like this. So we could show that if the original characteristic pair satisfy the GCD condition, then the new Toric orbifold coming from the wedge of this characteristic pair is also torsion-free and concentrated in even degree. So we claim that this new cohomology of wedge of this original orbifold, whether this cohomology is torsion-free or concentrated in even degree, we can detect this property from the less amount of combinatorics than the half dimension. Okay. So, okay. So this is my theorem. I probably many of you feel very unpleasant. I don't know. Feels. I can't see anybody smiling, but anyway, if I summarize everything, then please ask me if you need a non-trivial example of orbifold with this property in arbitrary dimension. I can give you. Thank you.
So the wedge operation in this case, the proof was like it's also Mayer-Vittori sequence. You are similar method.
Yes.
Of the previous.
Yes.
So the only difference is you have.
Yes, the length space bundle.
Yes.
Yes.
The length space.
Yes.